Hello, my name is Carlos Hernandez, and I have been invited by Scott Roberts and Explore Scientific to present a lecture on observing the planet Jupiter. As we all know, Jupiter is the largest planet in the solar system and is referred to as the king of the planets. Jupiter is, in mythology, the king of the gods. Jupiter is the Roman name for the king of the gods, and in Greek, it is Zeus. And he was the ruler of all the gods, and he had a powerful lightning bolt that he used to eliminate a lot of his enemies at the time in mythology. Jupiter is the largest planet, as I said a moment ago. It is the fifth planet from the sun. It orbits at an average distance of approximately 484 million miles or 778 million kilometers, which in astronomical units, which is equal to 93 million miles or 150 million kilometers. That's one astronomical unit. Jupiter is located at approximately 5.2 astronomical units from the sun. It orbits the sun in a period of approximately 12 years, exactly 11.9 years, and therefore it is located within each zodiacal constellation yearly as its orbit coincides with the number of zodiacal constellations. Jupiter is made up mostly of hydrogen, 90%, and helium, 10%, and trace elements including ammonia, methane, and very little water vapor, and hydrocarbons including ethane and benzene. Here we see a slide showing the comparison of Jupiter on the left and the Earth on the right. You could fit almost 12 Earths across the equator of the planet Jupiter. If you could hollow out Jupiter like a pumpkin, you could fit over 1,300 Earths inside of it. As you can see, when you look at Jupiter in a telescope, you will notice light zones and dark belts across the disk of the planet. And these belts and zones have different names according to their position over the globe of the planet Jupiter. On top, we see the North Polar region, and then we see a succession of interposing belts and zones. And you start with the North Equatorial Belt right above the equator, and you go up, and there's the North Tropical Zone, the North Temperate Belt, North Temperate Zone. Now, when you go above the North Temperate Zone and you see belts and zones, then you add another north or south nomenclature to it. So the next belt would be the north-north temperate belt or the north-north temperate zone. And this continues all the way up to the north or south polar regions of the planet. Jupiter has intense winds or jets that are located throughout the planet, and the greatest winds or jets are located over the equatorial zone of the planet and as well as the north tropical zone. Then as you go north or south, the winds decrease in velocity. Now, the winds also are located towards the east, which is considered prograde direction, and the winds that go westward are considered retrograde, and they can get up to 500 miles an hour. This is the diagram that I produced showing the different layers of Jupiter's upper atmosphere, the skin of the planet, showing the thermosphere at the top. Right below is the stratosphere, then the troposphere. Now, most of the clouds that we see when we look at Jupiter through the telescope are located within the troposphere, and that contains mostly ammonia ice clouds, but also ammonium hydrosulfide and other compounds that give the different colors to the clouds and belts of the planet. As you go in towards the core, the center of Jupiter, the pressures, as noted on the right, and the altitude on the left increases. So the lower you go into the planet, the temperature and the pressures increase to the point that at about 10 bars or 100 kilometers below the what's considered the 0 point or surface of the planet is at the point at which you have a pressure of 1 bar. 100 kilometers below that is where the gases become a liquid form. They transition into a liquid form at approximately this altitude in the atmosphere of the planet. As I mentioned, the zones and belts are noticed when you observe the planet. These zones are consisting mostly of ammonia ice clouds that are higher in elevation and cooler in temperature, whereas the zones are devoid of mostly of ammonia ice clouds and are lower in altitude but are warmer in temperature. So the zones, the air rises, and in the belts, the cool air sinks. At times, you have different eruptions over different parts of the planet, and a well-known eruption occurs over the south equatorial belt. As you can see in the section of a excellently detailed image by a friend, Christopher Go, you can see the development of a south equatorial belt disturbance, an SEB disturbance. And this occurs periodically, and it starts off as either a white or dark spot that continues to expand over a period of days to weeks until it encircles the entire belt. And below is a painting that I produced showing if you were located directly above that white spot erupting from below the atmosphere of the planet, you could see the main area to the right and then the leading cloud to the left. Here is a drawing of a south equatorial belt disturbance that I made on March 19, 2019, using my instrument, a 9-inch Maxitoff Cassegrain. And you can see the different parts of the disturbance. You can see as it appears in white clumps within dark areas between them. And this is considered a south equatorial belt or SEB disturbance. In 1995, NASA sent a probe into the atmosphere of Jupiter called Galileo. It went along with the Galileo orbiter that was orbiting Jupiter, and this is the first time that we were able to explore the atmosphere of a gas giant planet, in this case Jupiter. And it went into the entry point was located over the equator of the planet, and it descended into the planet. And as it descended, it took measurements of the different gases and temperatures of the planet as it descended. It transmitted data to the orbiter above for approximately 57 minutes before it was destroyed by the extremely high temperatures and pressures within the atmosphere of the planet. And that occurred on December 7th, 1995. A diagram showing the entry and descent of the Galileo atmospheric probe on December 7th, 1995. And it continued to transmit information all the way down to 140 kilometers below the 0 point of the atmosphere, or a pressure of 24 bars. The Great Red Spot is well known to most amateur astronomers, and it is an elongated anticyclonic vortex located over the southern hemisphere of the planet, and it measures approximately 1,300 kilometers in width and several hundred kilometers in height. Now, this is a cyclone or an anticyclonic vortex that have definitely been documented and observed and recorded since the late 1870s. Now, it may have been visible to astronomers as early as the mid 1600s, but we know for sure that it's been around since the 1870s. And it has a period, it rotates in a period of approximately 6 days, and the height of the top of the Great Red Spot is approximately 5 miles above the cloud tops, or 8 kilometers. But recent studies by the Juno orbiting spacecraft show that it extends as far as 500 kilometers below the top of the Great Red Spot into the atmosphere of the planet. A painting that I did of what it would look like if you were above the top of the atmosphere, adjacent to the Great Red Spot, and this is what you may witness if you were an astronaut floating within the atmosphere of the planet. Now, what we see when we observe the planet is the very outer skin of the planet, and that accounts for the zones and the belts. But as I mentioned earlier, as you descend into the planet, the gases become liquid. And as you descend, you encounter what's called metallic hydrogen, which occurs at extremely high pressures and temperatures. And this occurs all the way down until you get to the core of the planet, which is about 10 to 20 Earth masses in size. And that is the insides of Jupiter, and Saturn, Uranus, and Neptune are somewhat similar to this interior as well. Jupiter also has very faint rings that are not typically visible to the amateur or professionals from the Earth unless they image the planet in infrared wavelengths. But the Voyager spacecraft, when it flew by the planet in 1979 and 1980, it imaged these faint rings surrounding the planet. And Saturn, as we all know, with the beautiful ring system, but Uranus and Neptune also has a faint ring system as well. Jupiter has a total of 95 satellites or moons, and the largest of these are called the Galilean satellites, named after the discoverer Galileo Galilei, when he discovered them orbiting the planet with his primitive refractor telescope on January 7th, 1610. And you've got Io on the left, extreme left, followed by Europa, then Ganymede, and Callisto. Io is a fascinating satellite, and it's the closest of the Galilean satellites, and it has over 400 active volcanoes over its surface. And here's a painting that I did of what it would look like if you were able to stand over the surface of the planet with a sulfur volcano erupting and the lava lake below. And the reason that it is so volcanically active is that as it orbits Jupiter, the inside is stressed by tidal forces that heats the interior of the satellite, producing this molten lava, which then erupts onto the surface of the moon. The next satellite is a fascinating one called Europa. And we've heard a lot about Europa, that there's a possibility of a subsurface ocean, and who knows what possible life forms, if any, are present. But we are hoping to study this interesting satellite with the NASA Europa Clipper, which was recently launched and will arrive at Jupiter in 2030, followed by the European Space Agency's JUICE spacecraft, which will also study Europa, but also Ganymede and Callisto. And this is a painting I did showing the eruption of a geyser over the surface of the planet, with Jupiter visible in the background. The largest satellite of Jupiter and the largest satellite in the solar system is Ganymede, and is actually larger than the planet Mercury. So you've got a moon orbiting a planet that's actually larger than another planet. And it is also a very interesting planet that you can see groove and craters and other interesting surface features. And it too may have a subsurface ocean that will be studied by the ESA JUICE spacecraft in the near future. And it has aurora that visible over its poles, as well as you can see that the planet Jupiter has incredible aurora as well. This is my painting of the surface of Callisto, the outermost of the Galilean satellites, that is a very heavily cratered moon. And this is one of the surfaces area within one of the craters of the moon Callisto, and with Jupiter visible in the distance over the horizon. Jupiter will arrive at opposition on December 7th, 2024, and will be located within the constellation of Taurus, the Bull. And it will form a bright star in the core, in the center of Taurus, and it should be a spectacular sight in many telescopes. The tools that we use to observe Jupiter include instruments such as a refractor that uses the lens and a reflector that uses a mirror to form their images. These are two examples of the Explore Scientific refractor, an apochromat, or you can use a triplet, also more expensive but less color, better color correction. And the reflector, this is a Newtonian reflector that uses a parabolic primary mirror and a secondary flat mirror to produce the image. Other instrument designs used to study the planets, including Jupiter, include the Schmidt-Cassegrain telescope on the left. That's my Celestron 8-inch that I actually obtained in 1976, and I've used it well on the planets and deep sky objects, and it produces excellent images. The one on the right is my current instrument. It's a 9-inch Max-Hutov Cassegrain that employs both a corrector in the front and mirrors inside. The primary large one in the back, and then a smaller secondary over the corrector plate that reflects the images to the back of the instrument where you observe. Different eyepiece designs are very useful for observing the planets, including the Abbe orthoscopic at the top that uses 4 elements, and the popular fossil eyepiece in the middle that also uses 4 elements. And another well-known eyepiece for planetary observation is the Brandon eyepiece at the bottom that uses 4 elements as well. For my own observations, I like to use high-resolution eyepieces, and the advantage that I prefer using the Explore Scientific eyepieces is that they are also waterproof, besides being of high quality, producing sharp contrast images that allow me to see most of the detail on the planets. Useful accessories for observing Jupiter and the other planets and moon are the color filters. Now, using the different colors, you are able to pick out subtle features over the planet. The red filter might show you some dark condensations and the belts slightly better, as well as the orange filter. The yellow filter can be used to bring out bright features and some dark features. The green is good to show dark objects, including the belts and condensations. The blue and the violet are useful for the belts as well. Of all these, the ones that'll bring out the belts and the zones typically the best are the blue and the blue-green filters for observing Jupiter. We are at the mercy of the atmosphere on Earth, which is a blessing that it provides air for us, but it also is a blanket that waves at times because of the difference in temperatures. And we are affected, the images are affected by turbulence within the atmosphere. And this is a scale used to grade the seeing or the turbulence in the atmosphere that was developed by a Harvard astronomer, William H. Pickering. It's called the Pickering Seeing Scale, and it's from 0 or 1, which is the absolute worst, to 10, the absolute perfect steady image. Another scale was produced by the French Greco astronomer Eugene Antonati, and this uses a scale from 1 to 5, with 1 being a perfect image, 2 less perfect, 3 average, 4 poor, and 5 extremely turbulent and pretty useless to make an observation. Now you can use forms that you can produce your own or obtain from different organizations, including the Association of Lunar and Planetary Observers, ALPO, the British Astronomical Association, and the Oriental Astronomical Association as well, in order to produce a drawing of what you see, what you observe at the telescope. And this is an example of an observation of Jupiter that I made on March 3rd, 2004, using my 9-inch Max-Hutov Cassegrain at 257x, showing a wealth of detail over the planet. And this was made under very good seeing conditions, an 8 out of 10, or 2 on the Antonati scale. And you can see the great red spot located over the central meridian in the southern hemisphere as the telescope flips the image with south at the top and north at the bottom. And you can see the south equatorial belt North equatorial belt, and the different polar regions and other interesting features, including white ovals and dark condensations or spots. The image immediately to the right of the drawing is what's called an intensity estimate. And what you're doing there is using a scale from 0 to 10, where 0 is black and 10 is the perfect white. And here I've graded the different features that were visible according to how dark I perceived them over the planet at the time. Below that intensity estimate drawing is a sectional sketch that I focused specifically on the Great Red Spot region to show the wealth of detail that I was noting over the Red Spot and surrounding region at the time. And below it is numbers indicating the different longitudes. And Jupiter has 3 longitude systems. It's not a solid object, it's a gaseous planet. So the midsection, the equatorial zone from 7 degrees north or 7 degrees south, is called System 1, and that rotates in a period of 9 hours, 50 minutes, 30 seconds. And the regions north and south of the equatorial zone are called System 2, that rotate in a period of 9 hours, 55 minutes, and 45 seconds. The third system is called L3, and that's the rotation of the core of the planet, and that's considered the true rotation period, which is similar to the System 2, but different by a couple of seconds. A drawing of Jupiter that I made on November 11th, 2001, using an 8-inch Plazov Cassegrain that produced an excellent image showing the Great Red Spot, some blue festoons of the equatorial zone, and the north and south equatorial belts and polar regions of the planet at the time. You can also make a sectional sketch of the planet instead of making a full disk drawing, as Jupiter tends to get complicated at times because of the wealth of detail that you can see over the planet. So you don't actually have to make an entire disk drawing. You can do what's called a sectional sketch, and that's what I've done here, showing detail within the north equatorial belt on the planet on March 19, 2017. Sometimes if the seeing is adequately still, adequately well stabilized, you may be able to detect detail over the largest satellites of Jupiter. And this is a drawing that I made of detail that I noted over Ganymede on October 2nd, 2010. And the image on the right is a corresponding simulation using the NASA Solar System Simulator. And you can see very similar albedo bright and dark features over the moon that correspond with the simulator. So I wasn't able to resolve the detail that you would see with a spacecraft, but I could see that there was differences in brightness and darkness over the disk of the moon. Now, in 1994, mankind was treated to a show of cometary impacts over the southern hemisphere of the planet Jupiter, produced by the breakup of a comet that was once orbiting the planet called Shoemaker-Levy 9. And over a period of nearly a week, 23 fragments from the comet impacted the southern region of the planet and producing huge explosions that extended into the space above Jupiter. And the remnant of the debris, the scars of these impacts was visible to astronomers for weeks and months afterwards. A painting that I did of the eruption, the explosion, after an impact of one of the cometary fragments. If you're able to be in a spacecraft floating above the cloud top layers at the time. I was able to observe the impacts with my friends shown in this image with Tibi Dioria next to his telescope and Jeff Bache, which was the owner and producer of that telescope as well, a 16-inch f7 Newtonian that produced excellent images and allowed us to see a lot of the impact sites over a period of a week in July of 1994. These are drawings that I made, sectional sketches of the southern hemisphere and the impact sites produced by the comet fragments over that 7-day period in July of 1994. And if you observe the impact sites over a period of weeks, you would note the evolution or the spreading out of the material from the impacts. And it produced different shapes, and it was very interesting. Now, we have a spacecraft at this time orbiting Jupiter, obtaining measurements of the planet. And this is the Juno spacecraft orbiting the polar region. And you can see a spectacular aurora over the polar region while it's flying overhead. This is a painting that I produced of what it would look like if you were above the spacecraft orbiting the polar region at the time. As I mentioned earlier, the NASA is sending a spacecraft called the Europa Clipper that will be orbiting Jupiter, but it's going to be making close flybys of the moon Europa in order to determine that if it does have a subsurface ocean, how extensive the ocean is, and other characteristics of this fascinating moon that theoretically, but not proven, could harbor some form of life, a very basic life, but this is something that needs to be further evaluated, and that's why we're sending these spacecraft to explore this and other Galilean moons. And with that, I finished my lecture, and if you have any questions, please contact Scott Roberts at Explore Scientific, and I will be happy to answer whatever questions I may be addressed. Have a good evening. Thank you.